Boyle's law says that the pressure times the volume of a gas is equal to a constant, and this is assuming that it is an ideal gas. Real gases behave slightly differently, although it very closely approaches these values. And the constant is a constant associated with the pressure times the volume for a given closed system, which basically means that if everything else remains the same, such as the number of moles and the temperature, then the pressure times the volume is always going to equal some constant value, and the value of that constant is going to be dependent on the conditions of the system, such as the number of moles and the temperature. But if the conditions are constant, say if I had a gas inside of a cylinder like this, and this lid could move up and down. This lid's going to move up and down, so I can change the volume at will. And when I change the volume, the pressure is going to change, because if I give more space for the gas to move, then there will be less pressure, there will be less force exerting on this lid, because it will have greater area. Pressure is equal to force over area. So if the area increases, and the area can be thought of as a volume is a three-dimensional area essentially. So if the volume increases, then the force decreases, so the pressure will decrease. If I push this lid down and the area or volume decreases, then the force will increase, therefore the pressure will increase. And this law is just relating pressure to volume for a particular set of constant conditions. For example, just to show how this would work, suppose I have some pressure P, I'll change the color. Suppose I have some pressure P, some volume V, and I know that it's equal to a constant. And for argument's sake, let me just say the constant is just 1. It could be anything. It all depends on the temperature and the number of particles. If I were to double the pressure, what would happen to the volume? Well, if the pressure times the volume must always equal the constant 1, 2p must mean that I have to have 1/2 v to equal 1. And that's how this law is going to work, really. Let me give an example. Suppose I have, I'll just make up some numbers, 10 liters of gas at 1 atmosphere. And I go and I change the pressure, change it to, let me say I increase it to 5 atmospheres. What is the new volume? Now I go about solving this by saying I have volume 1 times pressure 1, and this is equal to a constant. But it's all in the same system. The system conditions are going to remain constant. I didn't change the temperature, I did not change the number of particles. So for this system over here, or this second set, it is also going to be equal to K. Second pressure and the second volume. Doesn't matter how I change these things. If I change one, if I change the volume, the pressure is going to adjust itself to be equal to the constant. If I change the volume, or if I change the pressure, then the volume will adjust itself to be equal to the constant. So since both of these are going to be equal to the constant, I can write it like this. And in fact, this is another way to write Boyle's law. I may see it written out like this, or I may see it written out like this, or I may even see it as volume is equal to K over P. There are many different ways to write out Boyle's law. But this is how I would get this version of Boyle's law from the original version. Since both of these are always going to equal the constant, I can just set them equal to each other. And now I can just go about filling this in and solving it. Volume 1 is 10 liters. Pressure 1 is 1 atmosphere. Volume 2 is my unknown, times pressure 2, which is 5 atmospheres. I'll multiply these out. I mean, this is a very simple problem. 10 liter atmospheres is equal to volume 2 times 5 atmospheres. Divide both sides by 5 atmospheres. 2 liters is equal to volume 2. And that's how I'm going to go about solving these various problems. The other gas laws are very similar, and then once I get to the, what's it called, PV equals nRT, whatever that other gas law that combines them all, combined gas law, there we go. Once I get to the combined gas law, it will also operate very similar to this, just with more variables.